Chapter IX. Cloud Formation (continued). As water in its condensed state is 815 times heavier than air, the question naturally comes to one why it does not immediately fall to the earth when it condenses. There are at least two, and probably more, stages of condensation. Investigators into the phenomenon of cloud formation claim to have ascertained that the first effect of condensation is to form little globes of moisture that are hollow, like a bubble, with very thin walls. Everyone has recognized the ease with which a soap bubble will float in the air, and yet it is simply a film of moisture. These little balloons, so to speak, are called spherules. It is undoubtedly the case that mingled with these little bubbles of moisture there are fine particles of solid water hanging on and carried along with them. Undoubtedly this is true. At least, just before the final act of condensation takes place, and when the little hollow spherules collapse, they are gathered together in drops of water larger or smaller according to the rapidity of condensation. There is probably another power at work to prevent the too ready precipitation of moisture when condensed, and that is the wind. A cloud never stands still, although in some cases it may appear to do so. If we take a stone in our hand and allow it to drop without applying any force to it, it will fall directly to the ground. But if we give it an impetus in a horizontal direction, it will travel some distance before striking the ground. If we could give the same impetus to a body as light as a globule of water dust, it would probably travel indefinitely without falling. Dust that would settle directly to the ground from an elevation in still air would travel thousands of miles without falling before a wind having any considerable velocity. Suppose the sun to be shining with intense heat upon a certain area of the earth's surface and the conditions to be right for very rapid evaporation of moisture. The air which is heated close to the ground, being expanded, will rise, together with the invisible particles of moisture, and there will be a column of moisture-laden air continually ascending until it reaches a point in the upper atmosphere where it is condensed into a cloud that takes on the billowy form which in summer time we call a thunder cloud, but which in the science of meteorology is called cumulus, or heap cloud. If there were no air currents, this billowy cloud would stand as the capping of an invisible pillar of ascending vapor, but as it is never the case that air is not moving at some velocity in the upper regions, it floats away as rapidly as it is formed. This peculiar kind of cloud is formed in the mid regions of the atmosphere, and it is a summer cloud as well as a land cloud. Of course, it may float off over the ocean and maintain its peculiar shape for a certain distance, but it is rare that such a cloud will ever be seen in mid-ocean or in midwinter. As the warm season advances in summer and evaporation from the earth is less than the rainfall, there is less and less moisture in the air, when, of course, the conditions for cloud formation, especially inland, are not so favorable as in the early spring or summer. Frequently there comes a time when we have a long season of dry, settled weather. Probably during most of the days clouds will form and we think it is going to rain, but before night they have vanished, and the same thing is repeated the next day and the next, perhaps for weeks at a time. The explanation is this. We have already said that so long as the air remains in a uniform condition as to temperature, it will absorb moisture in a transparent state until it is filled to the measure of its capacity at a given temperature. If there were no change of temperature, it would not condense into cloud. Clouds may be absorbed into the atmosphere, or evaporated, and become invisible, and this process is going on to a greater or less degree continually. If we watch the steam as it escapes from a steam boiler, the first effect is condensation into cloud, but as it floats away it gradually melts and is absorbed into the atmosphere as invisible vapor. This is especially true on a warm day. The same process takes place in the air that is going on at the level of a body of water or at the surface of moist earth. As before stated, condensation always takes place when a body of moisture-laden air comes in contact with cold. When the steam escapes from a boiler, even on the hottest day, it is hotter than the surrounding air. The first effect is condensation, and then evaporation takes place the same as it would at the surface of the earth when the condensed particles of moisture are separated into the invisible atoms that accompany evaporation. In settled, dry weather, as the sun approaches the zenith, the earth becomes intensely heated, and there is an ascending column of air partly laden with moisture, but not to the same extent as earlier in the season. Condensation takes place and clouds are formed, but as there is not sufficient moisture to carry them to the point of a further condensation, which would result in precipitation, as the sun lowers in the west and the heated air becomes more evenly distributed, this condensed vapor is reabsorbed into the air as invisible moisture by a process allied to that of evaporation. This condition of things would extend to a much longer period than it does in our latitude if it were not for the gradual changing of the seasons, which finally destroys the balance in the dynamics of cloudland and allows the cold, that has been held back for the time, in the great northern zone to get the upper hand. Then we have what is termed in common parlance a change in the weather, or, more properly in this case, a change in the season. We have already spoken of the cloud called cumulus, which means heap, and of its performance during the dry season of summer. There is another form of cloud that is seen at this season of the year called cirrus, a curl. It takes the form of a curl at its ends. This cloud usually has a threaded shape and sometimes takes the form of a feather, and frequently forms are seen that remind you of frost pictures on a window pane. These clouds float very high in the atmosphere, away above the tops of the highest mountains, from 6 to 8 miles above the level of the sea. They are formed only at a season of the year when the atmospheric conditions are most uniform. At certain times of the day and night the moisture will rise to this height before it condenses, and when it does condense it immediately freezes, which makes it take on these peculiar forms that would, no doubt, conform very closely to the frost pictures on the window pane, if it were not for the disturbing influences of air currents at this altitude. The fact that they are ice or frost clouds instead of water clouds gives them that peculiar whiteness and brightness of appearance. If ordinary clouds are water dust, these high clouds may be called ice dust. Sometimes we see them lying in bands or threads running across the sky in the direction that the wind blows. Their form is undoubtedly a resultant of the struggle between the air currents and the tendency of crystallized water to arrange itself in certain definite lines or forms. This cloud may be said to be one extreme, having its home in the highest regions of cloudland, while the cumulus or thunder cloud is the other extreme and occupies the lower or mid regions of the air. There is a still lower cloud, of course, as ordinary fog is nothing more than cloud, which under certain conditions lies on the surface of the ocean or dry land. Fogs prevail when the barometer is low. As soon as it rises from the source of evaporation, the moisture condenses almost to the point of precipitation. There is not enough buoyancy in its globules when the air is light, as it is when we have a low barometer, to cause the fog to float into the higher regions of the atmosphere. The high clouds, which are called cirrus, under certain conditions drop down to where they begin to melt into ordinary moisture globules, and while this process is going on we have a combined cloud effect which is called cirrostratus. This form of cloud may be recognized, when looking off towards the horizon, by its being formed into long straight bands. It is sometimes called thread cloud. As it further descends it takes on a different form called the cirrocumulus, or curl heap. This is just the opposite in its appearance to the cirrostratus, as it is broken up into flocks of little clouds separated from each other and in the act of changing to the form of the cumulus, or billowy form of cloud; and this latter takes place when it drops to a still lower stratum of warmer air, and is there called the cumulostratus, which is the form of cloud we most often see in the season of thunderstorms. The lower edge of the cloud is straight, parallel with the horizon, while the upper part is made up of great billowy masses having high lights upon their well-defined projections and blending into darker shades caused by the shadows in the valleys between the mountains of cloud. The rain cloud is called the nimbus, and may be said to be the extension of a cumulostratus. When it reaches this condition it is condensed to a point where the vesicular globules collapse and a number of them run together, forming a solid drop of water, and here it begins to fall. It may be very small at first, but in its fall other condensed globules will adhere to it, and if the conditions are right, sometimes the raindrops will have the diameter of 1/4 of an inch by the time they reach the earth. Under other conditions, such as we have sometimes during dry weather, the raindrops will start to fall, but instead of growing larger they grow smaller by absorption into the thirsty air, and will not be allowed to reach the earth. Often there are showers of rain in the air that fall to a certain distance and are taken up, as in the process of evaporation, to again be formed into cloud without ever having touched the earth. Thus it will be seen that clouds assume various forms under various conditions of atmosphere, as it is related to moisture, temperature, and density. Clouds sometimes appear to be stationary when they are only continually forming on one side and continually being absorbed into invisible moisture on the other. I remember seeing some wonderfully beautiful cloud effects in the regions of the Alps. Almost every day in summer there appears above the peak of Mount Blanc a beautifully formed cloud cap standing some distance above it and hollowed out underneath like an inverted cup. Although this cloud appears to be stationary, it is undergoing a rapid change. The moisture rises from the snow-capped peak as invisible vapor to a certain distance, where it is condensed into a cloud of wonderful brilliancy. As the cloud globules float upward, they are absorbed into the atmosphere again as invisible moisture at the upper limit of the cloud. If the wind happens to be blowing, another phenomenon takes place, giving the appearance somewhat of a volcano. It is blown off from the peak in the direction of the wind, but within a short distance it strikes a warmer stratum of air, where it is absorbed and assumes the transparent condition. If we ascend a high mountain, we get some idea of the altitude of the various forms of cloud. A thunderstorm may be in progress far below us, while the sun may be shining from a clear sky above, with perhaps the exception of the frost clouds that we have referred to floating high above the mountain tops. We have now described in a general way how clouds are formed, how they are condensed into rain, and how moisture is distributed over large areas by these rain clouds being borne on the wings of the wind. And now you ask, whence the wind? In our next and following chapters we will try to answer this question.
Chapter 10. Wind. Why it blows. We have said that the globules of moisture released by the action of the sun's rays in the process of evaporation tend to rise because they are lighter than the air. Right here let it be said that all material substances have weight. Even hydrogen, the lightest known gas, has weight and is attracted by gravitation. If there were no air or other gaseous substances on the face of the earth except hydrogen, it would be attracted to and envelop the earth the same as the air now does. Carbon dioxide is a gas that is heavier than the air. If we take a vessel filled with this gas and pour it into another vessel, it will sink to the bottom and displace the air contained in it until the air is all driven out. If we fill a jar with water up to a certain height and then pour a pint of shot into it, the water will be caused to rise in the vessel because it has been displaced at the bottom by the heavier material. Now, if we remove the shot, the water will recede to the level maintained before the shot was put in. On the contrary, if we should pour an equal bulk of cork or pith balls into the jar, the water would not be displaced because the balls are lighter than the water and would lie on top of it. If, however, the water is removed from the jar, the cork will immediately go to the bottom of the jar because the cork is heavier than the air which has taken the place of the water. We wish to impress upon the mind of the reader the fact that all substances of a fluidic nature, whether in the fluid or gaseous state, have weight and obey the laws of gravitation, and the heavier portions will always seek the lower levels, and in doing this will displace the lighter portions, causing them to rise. There is no tendency in any substance to rise of itself, but the lighter substance rises because it is forced to do so by the heavier, which displaces it. This law lies at the bottom of all the phenomena of air currents. If we are at certain points on the seashore in the summertime, we may notice that about 9 o'clock in the morning a breeze will spring up from the ocean and blow toward the land. This will increase in intensity until about 2 o'clock in the afternoon, when it has reached its maximum velocity, and from this time it gradually diminishes until in the evening there will be a season of calm, the same as there was in the early morning. The explanation of this peculiar action of the air is found in the fact that during the day the land is heated much more rapidly on its surface than the water is. The radiant energy from the sun is suddenly arrested at the surface of the earth, which is heated to only a very shallow depth, while in the water it is different. Being transparent, it is penetrated by the radiant energy to a much greater depth, and does not suddenly arrest it, as is the case on land. As the sun rises and the rays strike in a more and more vertical direction, the earth becomes rapidly and intensely heated at its surface, and this in turn heats the stratum of air next above it, which is pressing on it with a force of 15 pounds to the square inch at sea level. When air is heated, it expands, and as it expands it grows lighter. The stratum lying upon the earth, as soon as it becomes heated, moves upward, and its place is occupied by the heavier, cooler air that flows in from the sides. We can now see that if there is a strong ascending current of air on the land near the ocean, the cooler air from the surface of the ocean will blow in to take the place of the warmer and lighter air that is driven upward, really by the force of gravity, which causes the heavier fluid to keep the lowest level. As the earth grows hotter, this movement is more and more rapid, which causes the flow of colder air to be quickened, and hence the increasing force of the wind as the sun mounts higher in the heavens. But when it has passed the point of maximum heating intensity and the earth begins to cool by radiation, the movements of air currents begin to slow up until along in the evening a point is reached where the surface of the earth and that of the ocean are of equal temperature, and there is no longer any cause for the change of position in the air. The earth heats up quickly, and it also cools quickly, especially if there is green grass and vegetation. While they are poor conductors of heat, they are excellent radiators, so that when the sun's rays are no longer active, the earth cools down rapidly and soon passes the point where there is an equilibrium between the land and water. The water possesses the opposite quality. It is slow to become heated because of a much larger mass that is affected, and is equally slow to give up the heat. And the consequence is that after the sun has set, the land cools so much faster than the water that we soon have the opposite condition, and the sea is warmer than the land, which makes the air at that point lighter, and which in turn causes the denser or colder air from the land to flow toward the ocean and displace the lighter air and force it upward. Hence we have a land instead of a sea breeze, so that the normal condition in summer is that of a breeze from the ocean toward the land during part of the day, and a corresponding breeze from the land to the ocean during part of the night, with a period of no wind during the morning and evening of each day. The forces that work to produce all the varying phenomena of air currents on different portions of the earth are difficult to explain, as there are so many local conditions of heat and cold, and these are modified by the advancing and receding seasons. The unequal distribution of land and water upon the earth's surface, the readiness with which some portions absorb and radiate heat as compared with others, the tall ranges of mountains, many of them snow-capped, the lowlands adjacent to them that become intensely heated under the sun's rays, the diversity of coastline, and the fact that there is a zone of continually heated earth and water in the tropical regions, all these conditions, coupled with the fact that the earth rotates on its axis once in 24 hours, are certainly sufficient to account for all the complicated phenomena of aerial changes on the various portions of the earth's surface. The trade winds are so called because they blow in a certain definite direction during certain seasons of the year, and can be reckoned upon for the use of commerce. If you trace the line of the equator, you will notice that for more than 3/4 of the distance it passes through the water. The water, as we have explained in the last chapter, becomes gradually heated to a considerable depth, and when once saturated with heat is slow to give it up. It can easily be seen that there will be a zone extending each way from the equator for a certain distance that will become more intensely heated than any other parts of the earth, with the exception of certain circumscribed portions of the land. The result is that this heated equatorial zone is constantly sending up warm air caused by the inrush of colder air, which is heavier than the air at the equator, expanded by the heat. The warm air at the equator is forced up into the higher regions of the atmosphere, and here it overflows each way, north and south, causing a current of air in the upper regions counter to that of the lower. As it travels north and south, it gradually drops as it becomes cooler, and finally, at some point north and south, its course is changed and it flows in again towards the equator. As a matter of fact, the trade winds do not flow apparently from the north and south directly toward the equator, but in an oblique direction. On the north side of the equator, we have a northeasterly wind and a southeasterly wind on the south side. This is caused by the rotation of the earth from west to east. The direction of the trade wind, however, is more apparent than real. The earth in its diurnal revolutions travels at the rate of a little more than 1,000 miles an hour at the equator. But if we should travel northward to within 4 miles, say, of the North Pole, the surface would be moving at the rate of only about a mile an hour. At some point equidistant between the North Pole and the equator, the surface of the earth will be moving at a rate, say, of 500 miles an hour. If we could fire a projectile from this point that would have a carrying power to take it to the equator some time after the projectile was fired, although it would fly in a perfectly direct line, it would appear to anyone at the equator who observed its approach to be moving from a northeasterly direction. The reason is that the earth is traveling twice as fast at the equator as it is at the point whence the projectile is fired. Therefore, it will overshoot, so to speak, at the equator and not be dragged around by the increased motion we find there. To make this still plainer, suppose the earth to be standing still and a projectile to be fired directly across from the North Pole in the direction of the lines of longitude, and required 1 hour to reach the equator. The projectile would appear to anyone standing at the equator to come directly from the north. If, however, the earth is revolving at the rate of 1,000 miles an hour at the equator to the eastward, and the projectile was fired from the pole, where there is practically no motion, in the same direction along the longitudinal lines as before, the observer would have to be in a position on the equator 1,000 miles west of this longitudinal line in order to see the projectile when it arrived. Therefore, the apparent movement of the projectile would not be along the line at the instant that it was fired, but along a line that would cross the equator at a point 1,000 miles west. When a southward impulse is given to the air, it follows, to some extent, the same law, so that to one standing on the equator, the northern trade wind will blow from the northeast, and the southern trade wind from the southeast. Owing to the fact that the air rises in the heated zones, there is always a region of calms at this point where there is no wind and no rain. There are 2 other regions of calms in the ocean, one at the north, at the Tropic of Cancer, and another at the south, near the Tropic of Capricorn. As has been stated, there are currents flowing back in the upper regions at the equator north and south, and these are called the upper trades, the lower currents being called the lower trades. These upper trades gradually fall till they reach the Tropic of Cancer on the north, where the lower part of the current stops and bends back toward the equator, now becoming a part of the lower trade wind. This causes a calm at that point where it turns. The upper parts of this current continue on in a northerly and southerly direction on the surface until they meet with the cold air of the north and south polar regions, where there is a conflict of the elements, as there always is when cold and warm currents meet. The only point where the trade wind has free play is in the South Indian Ocean, and this is called the heart of the trades. If the whole globe were covered with water, there would be a more constant condition of temperature, but owing to the great difference between the land and water, both as to altitude and the ability to absorb and radiate heat, we have all of these varied and complicated conditions of wind and weather. The trade winds shift from north to south and vice versa with the advancing and receding seasons, due to the fact that the earth has a compound motion. It not only revolves on its axis once in 24 hours, but it rocks back and forth once a year, which is gradually changing the direction of its axis, and in addition to these motions, it is traveling around the sun as well. Chapter 11. Wind continued. In our last chapter we discussed the winds that prevail in the regions of the tropics called trade winds because they follow a direct course through the year, with the exceptions noted in regard to their shifting to the north or south with the changing seasons. We also described the phenomena of land and sea breezes, which during certain seasons of the year reverse their direction twice daily. We will now describe another kind of wind called monsoons that prevail in India. India lies directly north of the great Indian Ocean, and the lower part of it comes within the tropical belt lying south of the Tropic of Cancer. During the summer season here, the earth stores more heat during the day than it radiates or loses during the night. This causes the wind to blow in a northerly direction from the sea both day and night for 6 months each year, from April to October. During these months the land is continually heated day and night to a higher temperature than the water in the ocean south of it. The winds are probably not so severe during the night as through the day, as the difference between the temperature of the land and the water will not be so great during the night, and difference of temperature between 2 points usually means a proportional difference in the velocity of the wind. There is a time in the fall and spring while there is a struggle between the temperature of the land and water for supremacy, when the winds are variable, attended with local storms somewhat as we have them in the temperate zone. But after the sun has moved south to a sufficient extent, the land of India loses more heat at night than is stored up in the day, hence the conditions during the winter months are reversed. The water is constantly warmer than the land, and there is a constant wind blowing from the land to the ocean, which continues until April, when, after a season of local storms, the conditions are established in the opposite direction. These winds are called monsoons. The word monsoon is probably derived from an Arabic word meaning seasons. It is a peculiarity of this monsoon that in summer it blows in a northeasterly direction from the sea, and in the winter in a southwesterly direction from the land. This divergence from a direct north and south is caused by the rotation of the earth, and the explanation is the same as that we have given for the trade winds. In the southern latitudes there is a comparatively constant condition of wind and weather, because the surface of the globe in these regions is mostly water. But in the north, where most of the land surface is located, we have a very different and very complicated set of conditions as compared with the southern zones. The freaks of wind and weather that we find prevailing upon the North American continent are not so easily accounted for as the phenomena heretofore discussed. In the northern part the land reaches far up toward the North Pole, while on the west lies the Pacific Ocean, which merges into the Arctic Ocean at Bering Strait. The climate of the western coast is affected by a warm ocean current that sets up as far north as Alaska, while high ranges of mountains prevent the effects of this warm current from being felt inland to any great extent, all of which helps to complicate any theory that may be advanced regarding changes of weather. Aside from the changes of temperature that are due to the seasons, which are caused by the oscillating motion of the earth between the limits of the Tropic of Cancer on the north and the Tropic of Capricorn on the south, there are other changes constantly taking place in all seasons of the year. While it is not difficult to account for the change of seasons and the gradual change of temperature that would naturally follow, owing to the difference of angle at which the sun's rays strike the earth, it is more difficult to account for the violent changes that occur several times during the progress of a season, as well as the less violent ones that come every few days. In fact, it rarely happens that the temperature is exactly the same on any two successive days during the summer. The diurnal changes are easily accounted for by the rotation of the earth on its axis each day. But there is another class of phenomena with which the weatherman has to struggle when he is making up a forecast of the weather from day to day. In order that we may proceed intelligently, let us say a word about the barometer. We speak of high and low barometer, and we make the instrument with graduations marked for all kinds of weather, which really mean but very little. The reading of a single barometer alone will give us but a faint idea of what is really going to happen from day to day. But if we have a series of barometers located at different stations scattered all over the continent and connected at headquarters by telegraph, so that we can have the readings from a whole series of barometers at once, then it becomes a very useful instrument. A barometer may read low at one station by the scale, but may be high with reference to some other barometer that reads very low. What is a barometer? If we should take a glass tube closed at one end, the area of the cross section of which is 1 inch square, and fill it with mercury, and while thus filled plunge the open end into a vessel of mercury, it will be found that the amount of mercury remaining in the tube above the level of the mercury in the vessel will weigh about 15 pounds, if the experiment has been performed at sea level. This will vary, however, according to the temperature of the air. Of course, barometers are tested when the air is at a certain temperature. If the weight of the mercury in the tube is 15 pounds, since it is sustained by the air pressing down on the mercury in the open vessel, it shows that the air pressure on that open vessel is equal to 15 pounds to the square inch. In practice, of course, the tubes are made very much smaller. If the air changes so that it is lighter than normal, the mercury will fall into the tube, because the pressure on the mercury in the open vessel is less than 15 pounds to the square inch. And again, conditions may arise that will condense the air and make it for the time being weigh more than 15 pounds to the square inch, in which case the mercury will rise in the tube. Thus it will be seen that the barometer will register the slightest change in air pressure. Let us dwell for a moment on the causes of what are commonly called changes of weather, when we will again revert to the use of the barometer. The use of the telegraph in connection with the establishment of a weather bureau having stations for observation at convenient points throughout the country has contributed much to the science of meteorology. It is found that there are areas of high and low pressure existing at the same time in different parts of the country. These usually have their origin in the far northwest and follow each other, sweeping down the eastern side of the Rocky Mountains and gradually bending easterly and from that to northeasterly by the time they reach the Atlantic coast. The areas of low pressure are called cyclones, while the areas of high pressure are called anticyclones. By cyclone, we do not mean those cloud funnels commonly called by that name that form at certain times of the year in certain sections of the country and produce such destruction of life and property. These storms are usually confined to a narrow strip and are short-lived. They arise undoubtedly from local conditions. A description of these tornadoes, for such is their true name, will be given in some future chapter. These centers of high and low pressure may be several hundred miles apart. In the area of high pressure, if it is in the winter season, the weather is unusually clear and cold, and generally clear and fairly cool at any season, while there may be some wind it is not so strong as in the cyclone or low pressure center. At this point it will be warmer and winds will prevail, with rain or snow, the winds varying in direction and intensity at a given point as the cyclone moves forward. In the center of these cyclones and anticyclones, there will be a region of comparative calm, and the air is ascending at the center of the area of low pressure, while it is pouring in on all sides from the area of high pressure, where the air is compressed by a downward current from the upper regions. The high pressure or anticyclone system usually covers a larger area than the low pressure system, where the air is ascending. While the air moves laterally from high to low, it does not move in a direct line. The air movement outside of the high pressure center is usually not at a very high speed, but in northern latitudes in the direction of the hands of a clock. As it circles around, it widens out spirally until it reaches the edge of a low pressure system, when it bends in its course and moves in the other direction and around this center, but constantly moving inward toward it in a spiral form and in a direction that is reversed to that of the hands of a clock. When the air current comes within the influence of a low pressure system or cyclonic system, the velocity of its movement is very much accelerated until it has moved into the zone of quiet air in the center, where it is ascending. In the upper regions of the atmosphere there are countercurrents flowing in the opposite direction. The downward flow at the area of high pressure compresses the air near the surface of the earth and rarefies it in the higher regions of the atmosphere, while the opposite effect is going on over the center of low pressure, the air being rarefied nearer the surface of the earth, but condensed above normal in the higher regions by the upward current, which causes an overflow back toward the rarefied upper regions over the area of high pressure. It will be observed that the ordinary storm has a compound motion. The whole system moves in an easterly direction, while the winds are blowing spirally about the storm center. If we should be in the track of a moving storm so that its center passed over us, the winds at the beginning would blow in one direction, and then there would come a subsidence until it had moved forward to the quiet zone, when we should feel the winds in the opposite direction until the area of low pressure had moved forward into the region of high pressure. The velocity of the wind will be determined by the difference of pressure between the areas and by the distance that the areas of high and low pressure are apart. The steeper the grade, the more rapidly the fluid will flow. Let us now have recourse for a moment to figures 1, 2, and 3 in order that the subject may be more fully understood. In looking at these diagrams, we should imagine ourselves looking south with the left hand to the east. Figure 1 shows the general direction of the air movement between two areas, one of high and the other of low pressure. The arrows show the general direction of the wind. You will notice that in the upper regions it blows in an opposite direction from the air movement on the surface of the earth. Figure 2 shows in a general way how the wind moves spirally around both centers. Over the area of high pressure, the air descends spirally from the upper regions, circling around a large area. It may be 100 miles or more in diameter in the direction of the movement of the hands of a clock. But then the wind at the high pressure area is lighter than it is at the low, and circles outwardly until it finally moves off in the direction of a low pressure area, gradually bending in the other direction until finally it moves the reverse of the hands of the clock, although now it is in a smaller circle and with more rapid motion. It moves spirally and upwardly about the low pressure area until it reaches a point in the upper air where it goes through the same gyrations in an opposite direction. Now imagine the whole combination moving from west to east at an average rate of 30 miles per hour, and imagine further that this system is linked to other systems that are following along, and you will have some idea of the weather changes as they occur in the middle United States. By referring to Figure 3, you will see why the wind changes its direction when a storm center passes over any point. It has not only a spiral, but also a forward movement. Now let us go back to the barometer and see what part it plays in predicting changes in the weather. At the area of low pressure, the air is ascending, as we have seen, and owing to the peculiar way it ascends, by circling spirally upward around a region of comparative calm, it creates a partial vacuum, which is more pronounced in the center of the area. At the area of high pressure, the air will be condensed by the descending current being arrested by the earth. The descending current, coming as it does from the upper and colder regions, accounts for the cool weather that most always prevails at a high pressure area. In order to know how great the change of weather is likely to be, we must know what the readings of at least two barometers are, one at the high and another at the low pressure area. If the difference between the readings of the two barometers is very great, and the areas are comparatively close together, we may expect the change to be sudden and violent. High and low, as applied to a barometer, are only relative terms. There is no fixed point on the index of the instrument that can be said to be arbitrarily high or low. For this reason, a single barometer is not of much use. If it begins to fall from any point, and falls rapidly, it indicates that an area of a much lower pressure is approaching. The same is true of a high pressure area if the barometer rises rapidly from any point. If we study the air motions in these systems sufficiently to get at least an inkling of the law of their movements, it becomes a very interesting subject. Wind, from whatever cause, serves a wonderfully useful purpose in the economy of nature. Without wind, heat and moisture could not be distributed over the face of the earth, and our globe would not be a fit habitation for man. How wonderful is the machinery of nature that can first forge a world into shape, and afterwards decorate it with green grass and flowers that are watered by the early and latter rain.
Chapter 12. Local Winds. There are so many causes that will produce air motion that it is often difficult to determine just what one is the chief factor in causing the direction of the wind at any particular time. There are very many instances, however, where the cause can be traced without difficulty. Many of these have already been mentioned, and there are many more that might be. Of course, as has been often stated, there is only one remote cause for all winds, and that is the sun, coupled with the movements of the earth. But there are certain local conditions that are continually modifying the phenomena of air movement. The velocity of winds, as they occur from day to day, varies very greatly with the height above the surface of the earth. Ordinarily, the velocity at 1,000 feet above the earth will be more than 3 times greater than it is at 50 or 60 feet above, and even at 60 feet the velocity is much greater than at the surface of the earth. This is due partly to the retarding effect of friction caused by contact of the air with the earth's surface, but more particularly by trees, inequality of surface, and other obstructions on the earth. There is a variety of wind called mountain winds that arise from different causes. As has been stated in a former chapter, under ordinary conditions the air is more dense at sea level than at any point above, and the density is constantly changing from denser to rarer the higher we ascend. Suppose at a certain point, say halfway up a mountainside, the air has a certain density, and if it is at rest, the lines of equal density or pressure will seek a level, just as water would under the same conditions. Suppose we start at a given point on the side of a mountain and run out on a level till we are 100 feet in a perpendicular line above the side of the mountain. The air contained within those lines will be in the shape of a triangle. If now the sun shines upon the side of the mountain, the air is warmed and expands according to a well-known law, and the amount of expansion will depend upon the depth of the volume of air. Hence, the point of greatest expansion in our figure will be where the air is 100 feet deep, and will gradually decrease as we go toward the mountain till we come to the point where our horizontal line makes contact with the mountainside. At that point, of course, there is no expansion, because there is no depth of air, and the effect will be that the expanded air will overflow toward the mountain and be deflected up its sloping side. If we apply this same principle to the whole mountainside, we can see that there will be, during the day, a constant current of air flowing up the mountain. As night comes on, this upward movement will cease, and there will be a season of quiet until the earth has become colder than the air, and we have a phenomenon of exactly the opposite kind, when the air contracts instead of expands, which produces a downward current from the mountain top. These currents are as regular at certain seasons of the year as the land and sea breeze. Of course, they may be obliterated for the time being by the presence of a stronger wind due to some other cause, such as during the prevalence of a storm. In some of the regions of California hottest during the daytime, the nights are made endurable and even delightful by the cool breezes that sweep down from the tops of the mountains. It often happens that on the shady side of a high and steep mountain where the sun's rays strike it so obliquely, if at all, that the earth will be but little heated, there will be a vast mass of cold air stored up. After the valley has become intensely heated by the sun, there is an ascending current of air which in turn causes a downrush of the cold body of air from the mountainside. These local winds are frequently very severe, only lasting, however, for a short time until an equilibrium of temperature and density has been established. A wonderful exhibition of this sort of wind is said to occur at certain times of the year on the coast of Tierra del Fuego, where a blast which they call the Williwaws comes down from the mountainside without warning with such tremendous force that no ship could stand the strain if it should continue for any length of time. Fortunately, the shock does not last more than 8 or 10 seconds, when it is followed by a perfect calm. It is as though a great volume of air had been fired from some enormous cannon from the top of the mountain to the sea. The water is pulverized into a spray that is driven in every direction. Sometimes these violent blasts occur in the Alps, but from a very different cause. Avalanches of great extent often take place on the sides of the mountains, when a vast amount of material, equal to 300 or 400 million cubic feet of earth, will fall several thousand feet. Often an avalanche of this kind will produce a wind which is confined, of course, to a restricted area, that is said to be so violent as to tear one's clothes into shreds. This is not caused by any difference of temperature, but by a violent compression. There is a peculiar wind that occurs in Switzerland often between the months of November and March. These winds last from 2 to 3 days and are of great violence, especially near the mountains. They are warm and dry and are caused by an area of low barometer and an ascending current of air occurring at some point north of the Alps, which causes the air from Italy to flow over the Alpine range, causing a tremendous precipitation of snow and rain, which not only takes the moisture from the air, but sets free in the form of heat the energy that was stored in the process of evaporation, and this, together with the compression of the air as it flows down the slope of the mountains, makes it hot and dry. This wind is called the Föhn. There is a similar condition of things existing on the eastern slope of the Rocky Mountains, which has a modifying effect upon the climate of parts of Colorado, Wyoming, Montana, also extending up into British America. This wind, which is here called Chinook, rises from causes similar to those that are active in Switzerland that give rise to the Föhn wind. There is a wind called the blizzard that is felt most keenly in Montana and the Dakotas during the winter, which is exceedingly cold and lasts sometimes for a period of 100 hours. The temperature falls at times 30 or 40 degrees below zero, and the wind maintains a velocity of from 40 to 50 miles an hour. These winds spread eastward as far as Illinois, but not with the same severity, and they move southward to the Gulf of Mexico, spreading over the states of Texas and Louisiana, and are there called northers. It is exceedingly dangerous to be caught in a blizzard in the Dakotas, where the wind reaches its greatest velocity and the cold its lowest temperature, especially when the wind is accompanied, as it frequently is, by severe snowing. By the time it reaches the Gulf states, it is very much modified as to temperature, but it is a very disagreeable wind in that portion of the country, because of the exceeding dampness of the air. One would be much more comfortable in dry, still air, even if it were many degrees below zero, than in an air freighted with moisture, although the temperature has not fallen to the freezing point. There are hot winds called by different names according to the localities in which they occur. In Southern California, at certain seasons of the year, the inhabitants are afflicted with what they call a desert wind that blows from the heated regions of Arizona toward the Pacific Ocean. The temperature sometimes reaches 120 degrees Fahrenheit, and persons have been known to perish from the effects of these hot winds in open boats out on the water before they could reach land. Hot winds prevail on the plains of Kansas during the months of July and August that are phenomenal in their intensity, so much so that if they were widespread and of long continuance, like the northern blizzard, they would be attended with great loss of life and destruction to vegetation. Fortunately, they come in narrow streaks, and in most cases do not blow more than from 10 to 30 minutes at a time. These hot belts are sometimes not over 100 feet wide, and again they are as much as 500. They are so hot and dry that green leaves and grass are rendered as dry as powder in a few minutes. These winds are probably caused by the fact that at this season of the year, when the prevailing wind is southwesterly, the air becomes heated to a great height, and are the resulting effect of certain combinations of air currents in the higher regions of the atmosphere that force the already heated air towards the earth. As the air descends, it is more and more compressed, which causes it to become more and more heated. We have already described the heating effect of compression upon air as shown by the experiment with the fire syringe. It was shown that air at normal temperature could be suddenly compressed into so small a space that the condensed heat, which was before diffused through the whole bulk of air at normal pressure, was sufficient to cause ignition. A cubic yard of air on the surface of the earth would occupy a much larger space if carried a mile above it. From this it is easy to see that if a volume of air at that height had a temperature of 70 or 80 degrees, it would be very hot when condensed into a very much smaller volume, as it would be if it were forced down to the surface of the earth. These winds are the result of some superior force that is active in the upper regions of the atmosphere, because it is natural for heated air to rise, and this is what happens when the power that forced it down to the earth is no longer active to hold it there. Reference has been made in a former chapter to tornado winds. They are rather exceptional phenomena and not thoroughly understood. The winds seem to blow in from all directions toward an area of very low pressure at a single point. The spiral motion that is common to all cyclones in a tornado seems to be gathered up into a condensed form, like a funnel. The direction of movement is the same as that of the cyclone, that is, in the reverse direction to that of the hands of a watch. The upward motion of the air inside the funnel is at a rate of over 170 miles an hour. The onward movement of the whole system is about 30 miles per hour. Tornadoes occur with greater frequency in the United States than in any other section of the globe. Tornadoes seldom occur in winter, except perhaps in the southern states. They are more frequent in the month of May than at any other time during the year, although they occur sometimes in April, June, and July. Between 1870 and 1890, about 65 destructive tornadoes occurred in the United States, involving great loss of life and property. When a tornado moves off the land onto the ocean, it may become what is termed a waterspout. These probably never originate on the water, but after they have once formed may be carried over the water to a considerable distance. A tornado was never known to originate on the shores of Lake Michigan, but there are a few instances, the most notable one being the Racine tornado, when they have reached the lake after having traveled from some distant point inland. The Racine tornado, so called because it destroyed a large portion of that city, happened 15 or more years ago. The tornado originated about 100 miles southwest of Racine, Wisconsin, in northern Illinois. The funnel-shaped cloud passed over the lake, but the tornado character of the storm was broken up before it reached the other shore. When a tornado passes from land to water, it becomes a waterspout only when the cloud funnel hangs low enough and the gyratory energy is sufficiently great. There is a great pressure on the water outside the funnel and almost a perfect vacuum inside. This latter fact contributes largely to the destructive power of the tornado. When a funnel is central over a building, a sudden vacuum is created outside of it, and it bursts outwardly from the internal air pressure. Chapter 13. Weather Predictions. To predict with any great accuracy what the weather will be from day to day is a somewhat complicated problem, and, as all of us have reason to know, weather predictions made by those who have the matter in charge and are supposed to know all about it often fail to come to pass. The real trouble is that they do not know all about it. There are so many conditions existing that are outside of the range of barometers, thermometers, anemometers, and telegraphs that no one can tell just when some of these unknown factors will step in to spoil our predictions. In very many cases, perhaps in a large majority of them, the predictions made by the Weather Bureau substantially come to pass. It has been stated in former chapters that the changes of weather accompany the movements of what are called cyclones and anticyclones, the cyclone being accompanied by low barometric pressure and the anticyclone by a higher one. The winds of the cyclone move spirally around the center of lowest depression with an upward trend, the motions being in a direction reversed to that of the hands of a clock. In the centers of high pressure, the current is downward instead of upward, and the direction of wind around it is opposite to that around the low pressure area. The fundamental factor in predicting the weather is the direction of movement of those areas of low pressure. In almost all cases, the direction of movement is from the west to the east, but not always in a straight line. These movements, however, are classified so that after the direction has become established, one can predict with considerable accuracy as to whether it will move in a curved or a straight line. By movement, we do not refer to the direction of the wind at any particular point, but the onward movement of the whole cyclonic system, which is usually from 25 to 30 miles an hour, but in some cases the speed is much greater. Not only does the upward movement of the whole system vary, but the velocity of the wind around any given cyclonic center varies. There are about 11 classes of cyclones that appear in the United States, each class having its own path of movement and origin. A large number of these appear to originate north of the Dakotas and move directly east to the Gulf of St. Lawrence. 3 other classes originate on about the same line a little west, say north of Montana, moving first in a southeasterly direction, passing over the center of Lake Michigan and bending northerly through Lake Ontario, and finally landing in the Gulf of St. Lawrence. 2 other classes start at the same point, one of them going as far south as Cincinnati, the other as far south as Montgomery, Alabama, and both turning at these points northeasterly to the Gulf of St. Lawrence. 2 other classes originate in Colorado, one moving in a northeasterly direction, slightly curved, and the other directly east. Still others have their origin farther south in the Gulf of Mexico and move in a northeasterly direction. Very rarely they originate in the Atlantic east of Savannah, moving first in a northwesterly direction, but finally bending to the northeast. Every day there is a weather map made up showing the locations of the high and low barometers, direction of the wind, lines of equal pressure, as well as those of temperature. By study from year to year, all of these phenomena have become systematized, so that by tracing an area of low barometer from its origin and its progress easterly, it is soon seen to fall under one of these classes, and we are able to predict about what its course will be. Knowing the speed of its movement as well as the velocity of wind and all the conditions attending it, taken in connection with the weather conditions in the region for which the prediction is made, an expert can ordinarily forecast with some degree of accuracy. After all that can be said, however, weather predictions made upon maps are and have been far from satisfactory. One who has been a close student of local conditions for a number of years will often predict with as great accuracy as the Weather Bureau. Areas of low pressure are followed sooner or later by a fall of temperature. This is especially true in the winter months. Sometimes this fall is very marked, and then it is called a cold wave. These sudden changes of temperature are not thoroughly understood, but are supposed to be due partly at least to rapid radiation of heat into the upper regions, as the clear atmosphere which usually attends areas of high pressure is favorable to such a condition. Undoubtedly, too, there are dynamic causes, forcing the colder air from the upper regions of the earth, when it immediately flows off to an area of low barometer. Long-time predictions are purely guesses. They sometimes guess on the right side, and this gives them courage to make another. It is an old saying that all signs fail in dry weather. In time of a drought, it is true that the indications which at ordinary times would be surely followed by a rain are of no value. When a season is once established, either as a rainy season or a dry season, it is likely to persist in this character until a change comes that is produced by the movement of the sun in its course northerly and southerly, and the change produced from this cause requires several weeks of time. If accurate weather predictions could be made for a long time in advance, or even for a week, they would be of incalculable value. But it is doubtful if ever this will be brought about, as there are too many necessarily hidden factors which enter into the calculations. If stations could be established all over the oceans with sufficient frequency, and an equal number at a sufficient altitude in the air, I have no doubt that much that is now mysterious might be made plain.
Chapter 14. How Dew is Formed. Reader, did you ever live in the country? Were you ever awakened early on a summer's morning to go for the cows? Did you ever wade through a wheat field in June, or the long grass of a meadow, when the pearly dewdrops hung in clusters on the bearded grain, shining like brilliants in the morning sun? Have you not seen the blades of grass studded with diamonds more beautiful than any that ever flashed in the dazzling light of a ballroom? If not, you have missed a picture that otherwise would have been hung on the walls of your memory, that no one could rob you of. Everyone has noticed that at certain times in the year the grass becomes wet in the evening and grows more so till the sun rises the next day and dispels the moisture, and this when no cloud is seen. Dew is as old as the field in which grass grows. It was as familiar to the ancients as it is to us, and yet it is only about 3/4 of a century since the cause of it has been understood. We even yet speak of the dew falling like rain. In former times some scientists supposed that it was a fine rain that fell from the higher regions of the atmosphere. Others supposed it to be an emanation from the earth, while still others supposed it was an exudation from the stars. By his knowledge the depths are broken up and the clouds drop down dew. Proverbs chapter 3, verse 20. The first experiments carried out in a scientific way were by Dr. Wells, a physician of London, between the years 1811 and 1814. Everyone has noticed in warm weather the familiar phenomenon of water condensed into drops on the outside of a pitcher or tumbler containing cold water. This condensation is dew. It always forms when the conditions are right, summer and winter. In cold weather we call it frost. It has been stated in a former chapter on evaporation that the capacity of the air for holding moisture in a transparent form depends upon its temperature. If the temperature is at the freezing point, it will contain the 160th part of the atmosphere's own weight as aqueous vapor. If it is 60 degrees Fahrenheit, the air will retain 6 grains of transparent moisture to the square foot of air, while at 80 degrees it will contain nearly 11 grains. When the air is charged with this vapor to the point of saturation, which point varies with the temperature, a slight depression of the temperature is sufficient to condense this vapor into cloud or drops of water. Between 1812 and 1814, Dr. Wells made a series of experiments with flocks of cotton wool. He weighed out pieces of equal weight and attached a number of them to the upper side of a board and as many more to the lower side, and exposed it to the night air under varying conditions. One experiment was made with a board 4 feet from the earth, so that half of the bunches of cotton faced the ground and the other half the sky. He found upon weighing these after a night's exposure under a clear sky that the cotton wool on top of the board had gained 14 grains in weight from the moisture or dew that had formed upon it, while the same amount of cotton on the under side of the board had only increased 4 grains. He tried further experiments by making little paper houses or boxes to cover a certain portion of grass or vegetation. He found that while there would be a heavy dew on the grass outside, there was little or none within the enclosure. These experiments were conducted in various ways and closely watched to see that none of the phenomena were in any way connected with falling rain. It has been determined that substances like grass and green leaves of all kinds, hay and straw, while they are poor conductors of heat, are excellent radiators. In another chapter we have referred to this quality of straw that is taken advantage of by the inhabitants of hot countries in the manufacture of ice and in our own land for storing it. Perhaps everyone who has lived in the country has noticed that on a summer's morning, when the grass is laden with dewdrops, a gravel walk or a dusty road will be perfectly dry. This is due to the fact that the gravel will retain heat and not radiate it for a much longer time than grass or green leaves. Dew begins to form upon the grass very soon after the sun is set, because the moment the sun's rays are withdrawn, the heat is rapidly radiated by the blades of grass, which cools the earth under it and the air above and surrounding it, so that if the air is anywhere near the moisture saturation point, on cooling at the surface of the ground it will readily give up a part of its moisture, which condenses in drops upon the blades of grass. If the night is still and clear and there is much moisture in the air, the dew will be heavy, but if the night is cloudy, there will be little or no dew formed. The clouds form a screen between the earth and the upper region of the atmosphere, which prevents the heat from radiating to a sufficient extent to form dew. For the same reason, no dew will form under a light covering spread over the ground even at some distance above it. The covering acts as a screen, which prevents the heat from radiating to the dew point. From what has gone before, it will be seen that if the atmosphere is not charged with moisture up to the point of saturation, it will require a greater amount of depression of temperature to cause condensation, and this is why we usually have heavier dews in June, when the air is more highly charged with moisture, than we do in August, when it's dry. This also accounts for the ice clouds, called cirrus, being formed so high up in the atmosphere during dry weather. There is so little moisture in the air that it requires a very great difference of temperature to cause condensation to take place, and the necessary depression is not reached in these cases except at an altitude of several miles. Dr. Wells has shown that if we take the reading of 2 thermometers on a clear summer night, one of them lying on the grass and the other suspended 2 feet above it, we shall find that the one lying on the grass will read 8 or 10 degrees lower than the one suspended in the air. If the night is still, there will be a cold stratum of air next to the earth, which will not tend to diffuse itself to a very great degree, and dew will form. If, however, it is cloudy, or the wind is blowing, there is rarely any formation of dew. The reason in the former case, as we have explained, is that the radiated heat is held down to the earth in a measure, and in the latter case there is a constant charge of air, so that in either case no part of it is allowed to cool down sufficiently to precipitate moisture. It is a curious fact that often there will be a heavier dew under the blaze of a full moon on a clear night than at any other time. The moon has no screens about it of any kind to obstruct the free radiation of heat. It is supposed to be a dead cinder floating in space and not surrounded by an atmosphere, so that the sun's rays have full effect upon it during the time it is exposed to them, and at that time it becomes heated to a temperature of something like 750 degrees Fahrenheit. For half the month, say, the sun is shining continuously upon all or a part of it. In other words, the days and nights of the moon are about 2 weeks long. The moon does not revolve upon its own axis like the earth, therefore the same side, or a portion of it, is exposed to the sun for 14 days. During the time that the moon is in the earth's shadow, it is supposed to fall to 187 degrees below zero, which is 219 degrees below the freezing point. When the moon is full and is heated up to over 700 degrees, there is sufficient heat radiating from it to be felt sensibly upon the face of the earth, and it would be felt if it were not for the great envelope of atmosphere and its attendant cloud formations that surround the earth. There are but few days in summer when there is not a haze in the atmosphere, although we call the sky clear, which intensifies the light and gives everything a warmer tone. The heat coming from a full moon on a clear night is absorbed in causing the aqueous vapors that are partly condensed in the higher regions of the atmosphere to be reabsorbed into transparent vapor. This clears away the heat screen in the atmosphere and allows radiation to go on more rapidly at the earth's surface, and thus cools it to a greater extent when the moon is shining brightly than when it is dark and in the shadow of the earth. As we have already mentioned, the cold that is produced by radiation through the blades of grass and other radiating substances may be indicated by placing one thermometer on the ground and fixing another at some point in the air. Sometimes the difference is very marked, amounting to as much as 20 or 30 degrees. If under these conditions a cloud floats overhead, forming a heat screen, its presence will be readily noticed by a rise in the thermometer. Radiation into the upper regions of the atmosphere is checked, which causes a sudden rise in the temperature near the surface of the earth. By taking advantage of this principle of heat radiation from the earth's surface, it is a very easy matter to protect tender vegetation from even quite a severe frost, if it occurs in the early fall, by a slight covering, such as thin paper. The paper will act as a heat screen, and in a measure prevent the heat from radiating from the earth immediately under it. Frost, which of course is but frozen dew, at this season of the year will form on a still autumn night, although the atmosphere at some distance above the ground is some degrees above the freezing point. The reason for this will be obvious when we consider the facts that have been set forth concerning the power of radiation to produce cold. It has been estimated by meteorologists that the amount of water condensed upon the surface of the earth in the form of dew amounts to as much as 5 inches, or about 1/7 of the whole amount of moisture that is evaporated into the air. It will thus be seen that dew performs an important part in supporting vegetation. The same operation in nature's great workshop that forms the dews of summer creates the frosts of winter. The moisture in cold weather is condensed the same as in warm. When it is condensed at the surface of the earth, we have the phenomenon of frost, but when condensed in the upper regions of the atmosphere, we have that of snow. Heat radiation from the earth goes on in winter, which is evidenced by the fact that a thick covering of snow is a great benefit to vegetation as a protection against the injurious effects of frost. the writer has seen flowers blooming abundantly at an altitude of 12,000 feet above the sea level, protected only by the friendly shelter of a snow bank. In some cases the blooming flowers were in actual contact with the snow. By experiment it has been determined that the earth under a thick coating of snow is usually warmer by 9 or 10 degrees than the air immediately above the snow covering. Chapter 15. Hailstones and Snow. A hailstone is a curious formation of snow and ice, and most of the large hailstones are conglomerate in their composition. They are usually composed of a center of frozen snow, packed tightly and encased in a rim of ice, and upon this rim are irregular crystalline formations, jutting out in points at irregular distances. Frequently, however, we find them very symmetrically formed as to outline, and the snow centers are almost without exception round. Hailstones and hailstorms differ in different climates, but they are more pronounced in the torrid than in the temperate zone. Historians give accounts of hailstones of enormous size, the very large hailstones being undoubtedly aggregations of single stones that have been thrown together and congealed in the clouds during their fall to the earth. It is recorded that on July 4th, 1819, hailstones fell at Baconniere measuring 15 inches in circumference and very symmetrically formed with beautiful outline. Hailstones in India are said to be very large, from 5 to 20 times larger than those in England or America, seldom less than walnuts, and often as large as oranges and pumpkins. It is recorded that in 1826, during a hailstorm in Candeish, the stones perforated the roofs of houses like cannon shot, and that a single mass fell that required several days to melt, weighing over 100 pounds. It is further recorded that on May 8, 1832, a conglomerate mass of hailstones fell in Hungary, a yard in length and nearly 2 feet in thickness. Still another instance is recorded of a hailstone having fallen in 1849 of nearly 20 feet in circumference. This hailstone is said to have fallen upon the estate of Mr. Moffat of Ord. We will only ask our readers to listen to one more hailstone story, in which it is related that during the reign of Tipu, Sultan, a hailstone fell as large as an elephant. Undoubtedly one of two things was true regarding this latter story. It was either a very large hailstone or a very small elephant. The historian fails to give the size of the elephant. There is no doubt, however, but that hailstones may adhere and form large masses, owing to the violent agitation of the elements that always attends a hailstorm. Hailstorms are almost universally attended by constant and heavy thunder and lightning, together with violent winds. They usually occur on a very hot day and when the air is filled to saturation with moisture. When this is the case, a column of air is very highly heated at some point, when it ascends with great force into the upper regions of the atmosphere to a greater altitude than is common in the case of ordinary thunderstorms. Here it meets with an intensely cold body of air, when it is suddenly condensed, and readily frozen as soon as condensed, which not only forms hailstones, but sets free the energy that has been carried up in the moisture globules. This results in frequent electrical discharges, causing great waves of condensed and rarefied air, which, in the rarefied portions, produces still more intense cold, so that we have the condition for a mighty struggle between the elements, which is intensified by a constant and terrific electric cannonade. Undoubtedly there are also whirlwinds in the cloud, similar to those that sometimes visit the earth, which would tend to gather up the hailstones and aggregate them into large masses. It is a mighty battle between the moisture-laden, superheated air ascending from the surface of the earth and the powers residing in the upper regions of cold. Nature is constantly struggling to find an equilibrium of her forces, and the hailstorm is only one of the little domestic flurries that take place when she is setting her house to rights. Hailstorms are usually confined to very narrow limits, and they can prevail on a grand scale only in hot climates, where we have the conditions for wide differences of temperature between the upper and lower regions of the atmosphere, and also where the conditions are favorable for an enormous amount of absorption of moisture into the atmosphere. When snow is formed in the atmosphere, the conditions are quite different from those of a hailstorm. It is usually in a lower plane of the atmosphere, and there is no violent commotion, as is the case with the latter. A volume of air laden with moisture comes in contact with a colder volume of air when condensation takes place, as in the case of rain, except that the moisture is immediately frozen. In this case both volumes of air may be below the freezing point, but one is very much colder than the other. If the snow reaches the earth, it will be because the air is below the freezing point all the way down. Snow is formed at all seasons of the year. We may have a snowstorm on a high mountain when we have extreme heat at sea level. In summertime, of course, the snow melts as soon as it falls into a stratum of air with a temperature above the freezing point, and continues its journey from that point as raindrops instead of snowflakes. In the formation of a snowflake, Nature does some of her most beautiful work. A snowflake first forms with 6 ice spangles radiating from a common center. Shorter ones form on these 6 spokes, standing at an angle of about 60 degrees on each side of each spoke, of such length and arrangement as to form a symmetrical figure or flower. They do not always take the same form, but follow the same laws that govern the formation of ice crystals. The structure of a snowflake may be often found upon a window pane on a frosty morning. Here, however, the free arrangement of the parts of a snow crystal are interfered with by its contact with the window pane, but while floating gently in the air, there is the utmost freedom for the play of nature's forces as they apply to the work of crystallization. The difference in structure of snowflakes is chiefly due to the conditions under which they are formed. If the moisture is frozen too rapidly, the molecular forces that are active in crystallization do not have time to carry out the work in its completeness of detail, as it will where the freezing process as well as the condensing process goes on more slowly.
Chapter 16. Meteors. Meteors are the tramps of interplanetary space. They sometimes try to steal a ride on the surface of the earth, but meet with certain destruction the moment they come within the aerial picket line of our world's defense against these wandering vagrants of the air. They have made many attempts to take this earth by storm, as it were, and many more will be made. They fire their missiles at us by the millions every year with a speed that is incredible, but thanks to the protecting influence of the great ocean of air that envelops our globe, they become the victims of their own velocity. Meteors, or shooting stars, are as old as the earth itself, and they are the material of which comets are made. Before it was determined what these meteors or shooting stars were, many theories were promulgated as to their origin. One was that they were masses of matter, large and small, projected by volcanic action from the face of the moon with such violence as to be brought within the attraction of the earth. Others suppose them to be the effect of certain phosphoric fluids that emanated from the earth and took fire in the upper regions of the atmosphere. This, however, was mere speculation and without any scientific basis of fact. Anyone who has been an observer of shooting stars will have learned that there are certain periods of the year when they are more numerous than at other times, notably in August and November. Then again, there are longer periods of many years apart. By persistent observation it has been established that there are great numbers of schools or collections of cosmic matter that fly through interplanetary space having definite orbits like the planets. Any one of these collections may be scattered through millions of miles in length. A comet is simply one of these wandering collections of meteoric stones having a nucleus or centre where the particles are so condensed as to give it a reflecting surface, something like the planets or the moon. This enables us to see the outline of the comet to the point where the fragments of matter become so scattered that they are no longer able to reflect sufficient light to reach our eyes. The fringe of a comet, however, may extend thousands or even millions of miles beyond the borders of luminosity. There is scarcely a day or night in the year when more or less of these meteoric stones do not come within the region of our atmosphere, and when this happens the great velocity at which they travel is the means of their own destruction. They become intensely heated by friction against the atmosphere, just as a bullet will when fired from a gun, only to a greater extent owing to the greater velocity. They disintegrate into dust, which floats in the air for a time, when more or less of it is precipitated upon the surface of the earth. Disintegrated meteors, or star dust, as they are sometimes called, are often brought down by the rain or snow. Most of the shooting stars that we observe are very small, resembling fireflies in the sky, but once in a while a very large one is seen moving across the face of the heavens, giving off brilliant scintillations that trail behind the meteor, making a luminous path that is visible for some seconds. These brilliant manifestations are due to one of two causes. Either there is a very large mass of incandescent matter, or else they are so much nearer to us than in ordinary cases that they appear larger. It is more likely, however, that it is due to the former cause rather than the latter, from the fact of its apparently slow movement as compared with the smaller shooting stars. It has been determined by observation that the average meteor becomes visible at a point less than 100 miles above the earth's surface. It was found as far back as 1823 that out of 100 shooting stars 22 of them had an elevation of over 24 and less than 40 miles, 35 between 40 and 50 miles, and 13 between 70 and 80 miles. It was determined by Professor Herschel that out of 60 observations of shooting stars the average height of their first appearance was 78 miles, and their disappearance was at a point 53 miles above the earth. It is a matter of history, however, that sometimes these meteoric stones descend to the surface of the earth before they are entirely disintegrated. A fine specimen of this kind is to be seen in the Smithsonian Institution. There are over 40 specimens of these aerolites, airstones, in the British Museum, labelled with the times and places of their fall. Instances of falling to the earth are so rare that there is little to fear from these wandering missiles of the air. We do not remember a case where life or property has suffered from the fall of a meteor. This brings us to the consideration of the part which the great air envelope surrounding the earth plays as a protection against many outside influences. For instance, if it were not for the air, millions of these meteoric stones would be showered upon our earth every year and at certain times every day, which would render the earth untenable for human existence. We should be at the mercy of those wandering comets whose fringes strike our atmosphere more or less deeply at frequent intervals. It is not impossible that the earth may at some time pass directly through one, and yet there is little danger that in such a case there would be more than an unusual display of celestial fireworks. From the facts that have been above stated, it will be apparent to anyone that the number of these meteoric stones in the air is being constantly reduced by their constant collision with the atmosphere and consequent reduction to ashes or dust. Another conclusion is that the earth must be gradually, but imperceptibly perhaps, increasing in size on account of the constant settling upon its surface.
Chapter 17. The Sky and Its Color. In the chapters on light in Volume 2, it will be stated that we see all objects by a reflected light, except those that are self-luminous, such as the sun or any other source of light. We see the moon and many of the planets entirely by reflection. There are myriads of smaller objects, too small to be seen as such, even under a microscope, that still have a power to reflect light that is sensible to our vision. The air surrounding the globe is literally filled with these microscopic light reflectors. They serve to give us a diffused light which enables us to see clearly all visible objects. We have all noticed the effect of a single electric arc light, situated at a distance from any other source of light, and how it casts extremely dark shadows and very high lights, so much so that it is difficult to see an object perfectly in this light, because the part of the object that is under the direct rays of the lamp is so highly illuminated that the shadow, by comparison, has the effect of simply a dark blot without form or shape. Many of you have noticed in a country village, where the streets are lighted with electric arc lamps, what a difference there is in the illuminating effect between a clear and a foggy night. When there is fog, or when the clouds hang low down, we get a reflection from these, which tends to diffuse and soften the powerful light rays that are sent out by these lamps. This effect is especially noticeable when the night is only moderately foggy. Each globule of moisture floating in the air becomes a reflector of light, and by myriads of reflections and counter-reflections the light, which on a clear night is concentrated, is diffused over a large area, producing an illumination which for practical purposes is far superior to that produced on a clear night. When the latter condition prevails, the rays of light are so intense on objects immediately surrounding the lamps that one is blinded, so that the places which are in shadow seem darker than they would be if there were no light at all. The only way to prevent this is to have the lights set so close together that there will be cross lights, which tend to break up the intensity of the shadows. This principle of light diffusion is taken advantage of to produce an even illumination in stores that are lighted only on one or two sides. This is effected by a series of prisms or reflecting surfaces that are cast upon the panes of glass. If, now, there were no atmosphere, or to state it differently, if there were no floating substances in the atmosphere, the sun would produce an effect upon the earth similar to that of a single electric light. The lights would be extremely high and the shadows extremely dense. To one looking off into space, the sky, instead of having the blue appearance that we see, would have the effect of looking into a deep, dark abyss without illumination. Tyndall has shown us by a beautiful experiment that if there be in a glass tube a mixture of gases related to each other in a certain way chemically, they will combine into small globules or particles similar to moisture in the air. If, now, a beam of light is thrown upon this tube and a dark screen put behind it, we shall, in the beginning of the experiment, simply see the dark screen. As soon, however, as the molecules of the gases have combined in sufficient numbers to produce particles of sensible size, we begin to have a reflection of light from them, the color of which is constantly changing as the combining particles grow in size. At a certain stage in its progress, the color which the mixture of gases assumes is a beautiful azure blue, rivaling in purity the finest skies of Greece or southern Italy. The sun is the great lamp that illuminates the world, while the atmosphere, which is filled with particles of various substances, becomes the shade of the lamp which diffuses and softens the light, and gives it its color tones, whether of warmth or coldness. We could not well do without the reflected light of the sky. The poetry of life would be sadly marred. The beautiful effects of color and purity of tone would be wanting. We need to bathe in light as much as in water, and the character of the light is almost as important as the character of the water. Imagine a world with an atmosphere devoid of all substances that would in any way reflect light, or give to it softness or color tone. Imagine a sun or a moon without visible rays, for without a reflecting atmosphere there would be none. Imagine a sky that was no sky at all, but only a dark void with no protecting vault. Think of the shadows, so dark that you could see nothing in them. These would be some of the effects that would come from an atmosphere that had no sky substance in it. Imagine the world lighted by one great arc light. The reflex action upon the race living in such a light would be anything but desirable. The world would develop into an arc-light civilization, if one can imagine what that would be like. Certainly one of intensely violent contrasts. Look on this picture and let us be thankful for the blue sky and golden sunsets. But, you ask, why is the sky blue? In one of the chapters on the subject of light in Volume II, the properties of soap bubbles are discussed. It is shown that when a film is stretched across the mouth of a tumbler held in a position so that the film is perpendicular, by the action of gravity, the moisture constantly falling to the lower part of the film, it will continually grow thinner, and horizontal bands of color will appear on it, first red, then followed by the other colors of the solar spectrum, ending with violet. It is also stated that every color of light has a definite wavelength. Where a band of blue color appears on the film, we know that its thickness is right for the wavelength of that particular color, which is reflected from the back of the film to the eye. If we could conceive the blue vault of the heavens to be half a sphere of a soap bubble, the color that the sky would appear to us, if the light could be thrown upon it from beneath, would be determined by the thickness of this film. If the film was 1/156,000th of an inch, the sky would be red instead of blue. To reflect the other colors, the film would have to grow thinner for each color, in the progression from red to violet. The color of the sky is determined by a light reflection from the minute globules of moisture floating in the air. If the sky is blue, then the globules must be of the right diameter to reflect that color. The various tints and colorings of the sky are determined by what is found in the atmosphere, and this is the reason why skies differ in coloring and tone in different sections of the globe. The finest skies are probably found in semi-tropical regions like southern Italy, Greece, and California. In 1892 I visited Greece in the early part of June. In crossing the Adriatic from Brindisi to Patras in Greece, the route was through the Ionian Islands that are grouped along the southwestern shore of Albania. The sky was without a cloud, and its beautiful blue color was reflected in the waters of the Adriatic, and I never shall forget the impression made upon my senses when we first came in sight of the mountains on the west coast of Albania. At this point they rise abruptly from the water and are colored with that particular azure haze, mixing with a shading of warmth, which is an effect that distance gives in the classic atmosphere of old Greece. The effect upon the beholder is to intoxicate the senses, and to fill him with that deliciously poetic feeling that always comes when standing in the presence of the sublime in nature. It was not the mountains themselves that produced the effect, for I have seen grander than these, but it was the sky on the mountains. When we look at a distant mountain, it seems to be partly hidden by a peculiar haze that is the color of the sky at that time. We are really looking at the mountain through a portion of the sky. While in Athens, I took a trip to the top of Mount Pentelicus, which separates the plains of Athens on the south from those of Marathon on the north. From the summit of this mountain we have a most wonderful view of the archipelago of the Aegean Sea, a beautiful map of blue water and brown islands that melt together in the distance. At our feet lay the historic plains of Marathon, and in the distance rose the snow-capped peaks of Mount Olympus. It is doubtful if the world furnishes a more beautiful combination of ocean, island, continent, and sky than can be seen from Mount Pentelicus. Myriads of brown islands set in the bluest of water, graceful in outline and multiform in shape, jutting headlands and landlocked harbors, strong in color and outline in the immediate foreground, but gradually melting together in the distance, the brown becoming bluer and the blue a softer blue, till the whole is lost on the horizon in a sky that shades back to the zenith in an ever-changing azure that for purity of tone baffles all description. What wonder that a people born under such skies and whose eyes have feasted on such beauties in nature should conceive and execute such a masterful work of art as the Parthenon. While the variation of landscape, the stretch of water filled with islands, and the mountains capped with eternal snow were a prominent part of the picture, it was the sky with its beautiful color tones that, after all, gave it its wonderful charm. The skies in a northern latitude are colder and grayer, due to the fact that nearly always there is a certain degree of condensation of moisture existing, which, while it does not take the form of a cloud, still gives a toning to the sky. There is no doubt but that the color tones of the sky have an influence upon the character and temperament of the people who live under them. Under semi-tropical skies the poetic nature is more strongly appealed to, and a man is more likely to be controlled by his dreamy imaginings than his cold calculations. We find this latter characteristic prevailing to a greater or less extent among the people who live under colder and sterner skies. If all these qualities or influences could be combined in the right way, the race would be stronger intellectually and in other ways. It is always dangerous to a race of people to be developed along certain lines only. The development should be symmetrical. The strongest men are not those who are simply coldly intellectual, neither those who are simply emotional and sentimental, but those in whom heart, mind, and soul are so related that each one of these elements reinforces and strengthens the other. At certain seasons of the year and in certain localities, it is not uncommon to have wonderfully beautiful displays of coloring upon the skies and clouds at sunset. The question is often asked why we do not see these displays at other times in the day than at sunrise and sunset, for the same effects are seen in the morning, but they are not noticed so often, because to do so would interfere with the habits of the average man and woman. The reason for this change of coloring is the angle at which the sun's rays strike the clouds of an evening sky, which are reflected to our eyes. When the sun is high in the heavens it shines against the back of the clouds, from the point of view of a person standing on the surface of the earth. It also shines a shorter distance through the air at midday than at sunset. At sunset the rays are able to shine on the underside of a cloud, especially if it is high in the air. The moisture globules of which the cloud is made up are much larger than the transparent ones that are uncondensed and just as they were when released in the process of evaporation. As we have already seen, the reflections from these minute globules give us the blue coloring of the sky, and are very much smaller in diameter than a globule that is able to reflect the red ray. When these small globules are condensed into a cloud, a great number are combined into one globule, and they are of all sizes from the globule of evaporation to that of the raindrop when precipitation takes place. We have, then, in the various stages of cloud formation, all conditions present for reflecting the various colors and combinations of colors that are found in the solar spectrum. Hence it is that, under certain conditions of atmosphere and cloud formation, we see at sunset painted upon the sky those wonderful combinations of colors, more beautiful and delicate in shading, more various in combination and purer of tone, than any artist, however cunning his fingers or brilliant his pigments, has ever been able to truthfully reproduce. Even when the sky is cloudless, it often assumes a brilliant hue, which is partly a reflection from the invisible moisture globules and partly due to floating particles of dust that may have been driven up from the surface of the earth, or may be the ashes of meteorites disintegrated by contact with the air. Some years ago, commencing in August 1883, there was a wonderful exhibition of red skies at sunset that lasted for several hours after twilight ordinarily disappears. This phenomenon ran through a period of several weeks, gradually fading away. It was afterward determined that these displays were occasioned by small particles of ashes or dust floating high in the air, that were thrown off from the volcanic eruption of Krakatoa in the island of Java. By the general circulation of the air these ashes were carried to all parts of the world, making a circuit of the earth in from 12 to 13 days, which showed a velocity of over 80 miles an hour. This is an instance of the high velocity of the air currents in the upper regions of the atmosphere. The reason why the illumination extended so late into the night was because of the great height that these particles of dust attained. The higher the reflecting surfaces are in the air, the longer they may be seen after sunset. Ordinary twilight is caused by a reflection of sunlight from the upper air, and from its duration as ordinarily observed, it is estimated that the reflection does not proceed from a point more than 36 miles high. In the higher latitudes the twilight is long from the fact that the sun does not go directly down, and if we go far enough north, the whole night is twilight. In the tropical regions the twilight is shorter than at any other point on the globe, for reasons that are obvious. The sun there goes directly down, and is soon hidden behind the earth. There are other optical effects to be seen sometimes on the horizon somewhat resembling twilight. The aurora borealis, northern lights, which we describe in Volume III, is seen in the northern skies at certain times, and has very much the appearance of twilight in some of its phases. It is constantly changing, however, and is easily distinguished by anyone who has observed both. These appearances are undoubtedly electrical. There is another phenomenon seen in the Arctic regions that causes a band of white light to appear on the horizon called ice blink, and it is caused by the reflections from the great icebergs that abound in that region. Curious optical effects are sometimes observed a little after sunset in the form of streamers or bands of light that shoot up into the sky, sometimes to a great height. These are undoubtedly due to cloud obstructions that partially shut off the sun's rays from a part of the sky, but allow it to shine with greater brilliancy in the path of these bands of light. It will be seen from the foregoing that the sky in all of its phases is a product of sunlight and the substances that float in the air, including moisture, not only in the invisible state, but in all the stages of condensation, as well as particles of floating dust.
Chapter 18. Liquid Air. Air, like water, assumes the liquid form at a certain temperature. Water boils and vaporizes at 212 degrees Fahrenheit above zero, while liquid air boils and vaporizes at 312 degrees below zero. Heat and cold are practically relative terms, although scientists talk about an absolute zero, the point of no heat, and Professor Dewar fixes this point at 461 degrees Fahrenheit below zero. Others have estimated that the force of the moon during its long night of half a month is reduced in temperature to 600 or 700 degrees below, which is far lower than Professor Dewar's absolute zero. However this may be, to an animal that is designed to live in a temperature of 70 or 80 degrees Fahrenheit, any temperature below zero would seem very cold. If, however, we were adapted to a climate where the normal temperature was 312 degrees Fahrenheit below zero, we should be severely burned if we should sit down upon a cake of ice. Such a climate would be impossible for animal existence, for the reason that there would be no air to breathe, since it would all liquefy. Liquid air is not a natural product. There is no place on our earth cold enough to produce it. If the moon had an atmosphere, which it probably has not, it would liquefy during the long lunar night, for heat radiates very rapidly from a planet when the sun's rays are withdrawn from it. As you have already surmised, liquid air is a product of intense cold. Any method that will reduce the temperature of the air to 312 degrees Fahrenheit below zero will liquefy it. Great pressure will not do this, for we may compress air in a strong vessel until the pressure on every square inch of the vessel is 12,000 pounds, or 6 tons, and still it will not liquefy unless the temperature is brought down to the required degree of coldness. If this is done it will change from a gas to a liquid, but will occupy as much space as before if it is condensed to a pressure of 6 tons to the square inch. Until 20 years ago it was supposed that oxygen and atmospheric air, the latter a mixture of oxygen and nitrogen, were fixed gases and could not be liquefied. In 1877 it is said that Raoul Pictet obtained the first liquid oxygen, but only a few drops. About 15 years later Professor Dewar of the Royal Institution, London, succeeded in liquefying not only oxygen but atmospheric air, and besides liquefying the air he made ice of it. In 1892 I visited London, where I met Professor Dewar, who invited me to witness an exhibition of the manufacture of liquid oxygen, and incidentally liquid air, at the Royal Institution. To me it was a most wonderfully interesting event. I saw air, taken from the room, gradually liquefy in a small glass test tube open at the top. When the tube was withdrawn from the refrigerating chamber it boiled by the heat of the room and rapidly evaporated. We lighted a splinter of wood and blew it out, leaving a live spark on the end of it, and held it over the mouth of the tube, knowing that if anything like pure oxygen were evaporating, the splinter would relight and blaze. An old experiment with oxygen gas. At first the splinter would not relight, because the evaporating gases were a mixture of oxygen and nitrogen in the proportions to form air. But owing to the fact that nitrogen evaporates sooner than oxygen, a second trial was successful, for the splinter immediately began to blaze, showing that the gas evaporating then was pure or nearly pure oxygen. When the liquid oxygen was poured into a saucer, and brought into proximity with the poles of a powerful magnet, the liquid immediately rushed out of the saucer and clung to the magnet poles, showing that oxygen is magnetic. Since that time other experimenters have succeeded in making liquid air on a comparatively large scale, and the process is simple when we consider some of the old methods. Mr. Tripler of New York, who has made liquid air in great quantities, does it substantially as follows. First, he compresses air to about 2,500 pounds to the square inch. Of course the air is very hot when it is first compressed because all the air in the tank has been reduced in bulk about 166 times, and all the heat that was in the whole bulk of air is concentrated into 1/166 of the space it occupied before it was compressed. It is 166 times hotter. There are 2 sets of pipes running from the compressor to a long upright tank called the liquefier. These pipes pass through running water, so that the compressed air is quickly cooled down to the temperature of the water, about 50 degrees Fahrenheit. The pipes, at least one side of them, run the whole length of the liquefier, and most likely are coiled. This set of pipes contains the air to be liquefied. A second set of pipes runs to the bottom of the liquefier, where there is a valve. By opening this valve, a jet of compressed air is allowed to play on the other set of pipes, when intense cold is produced by the sudden expansion of the air. This cold air rushes up around the pipe containing the air to be liquefied, and escapes at the top, thus absorbing the heat until the temperature is reduced to 312 degrees below zero. Then the air liquefies and runs into a receptacle, where it may be drawn off at pleasure. It will be seen that a large part of the compressed air is wasted in cooling the remainder sufficiently to liquefy. The use to which liquid air may be put advantageously is an unsolved problem, but no doubt it will have a place in time. All great discoveries do. Electricity had to wait a long time for recognition, but what a part it plays now in the everyday life of the whole civilized world. Curious effects are produced by this intense cold. Meat may be frozen so hard that it will give off a musical tone when struck. Here is a pointer for the seeker of novelties in the line of musical instruments. Liquid air furnishes a beautiful illustration of the fact that a burning gas jet is continually forming water as well as giving out heat and light. If we put liquid air into a tea kettle and hold it over a gas jet, ice will form on the bottom from the water created by the flame, and it will freeze so hard that the flame will make no impression upon it, other than to make the ice cake grow larger. Although liquid air is not found in nature, and is therefore called an artificial product, it is produced by taking advantage of natural law. Without the intellect of man it never would have been seen upon this earth, and the same may be said concerning many things in our world, both animate and inanimate. The genius of man is godlike. He lifts the veil that shrouds the mysteries of nature, and here he comes in very touch with the mind of the infinite. Man interprets this thought through the medium of natural law, and lo, a new product! How much life would have been robbed of its charm and interest if all these things had been worked out for us from the beginning! For there is no interest so absorbing and no pleasure so keen as that of pursuit when the pursuer is reaching out after the hidden things that are locked up in nature's great storehouse. From time to time she yields up her secrets, little by little, to encourage those who love her and are willing to work, not only for the pleasure of the getting, but for the highest and best good of their fellows.